Hello everyone, welcome to another video of the course. In this video, we are going to set the two-dimensional model to do dynamic simulation of the motor. So let's delete this three-dimensional model. And here we have two-dimensional model. I saved the project in desktop, single phase induction motor. I write here new FEA file, save. So, and change the name of this design to dynamic simulation. I'm going to do dynamic simulation. So here I select this object. Let's change its name to a stator and set the material of this object. The stator and rotor lamination grade is M450A. So the material, the electric steel grade of the stator and rotor core is equal to this one, M450A. This, I select this and press K. We have rotor here. So select the same material and the name is rotor. I select the rotor and the stator and let's change the color. Right. So first of all, we should set the material composition type that is not solid is laminated. Direction of lamination is in the direction of the z-axis. So stacking direction is equal to V3. Stacking is in the direction of the z-axis. And I press OK. Yes. So the stator and rotor cores. Then I select the stator winding coils. I select all coils and set the material equal to, I write here Cooper, press OK. Excuse me. Let's select again. I write here Cooper and select this material, double click, right? And let's change the color. Right. Also, we have these objects that the material is aluminum. Select aluminum here and change the color. So we set the material of these objects. Now I should define excitations. I define first, I change the solution type to transient because I want to do a dynamic simulation. So I change the solution type to transient and I press OK. So from here, I add a winding that is phase A and another winding that is phase B. Phase A and phase B. I press OK. Here you can see the stator winding. Actually, this is the finite element model that we created using the SolidWorks. we created the geometry and imported this geometry. So this is the phase A and this is the phase B. Two identical coils, right? Two identical coils. Number of turns are also equal. So here, this is a two-pole machine, a two-pole single-phase induction motor. So you can see the winding here, right? We have 4 stator slots per pole in each phase, and you can see this is phase A and this is phase B. So you can see the end winding of one phase, right? So these two coils are this one and this one, this one and this one, right? You can see in this figure. So I select, not important, I select these 4 coils, these 4 coil arms, and I assign excitation. Coil, I write here, I should set number of turns in each conductor. Here you can see number of turns per coil, that is 500 NTC, number of turns per coil. All of 4 coils are in series in each phase. In each phase, we have 4 coils that are in series. So here you can see the number of turns per phase. Actually, I counted up number of turns per each coil using this method. After cutting the coil arm, one coil arm, we can count up number of turns in each phase, right? This is the process. So here I assign excitation, coil is 500 and the direction is positive. For example, I press OK. So I select phase A and add these 4 coils. Let me check. The phase A is not solid, is stranded. And also phase B is stranded. When we select a solid winding, the number of turns in the coil should be equal to 1. So I select phase A and I select this 4 coil arms, phase A, this 4 coil arms, assign excitation, coil 500, the polarity is negative this time. And again, I add these coil arms. So this is the phase A, right? This is the phase A. And also you can see direction of the current in the phase A. So because this is the direction of the current, or in this way, we have the polarity here is positive and polarity here is negative. This will be the magnetic axis of the phase A. And now let's create the coil arms for the phase B. I select this objects, coil 500 positive. Again, I select these coil arms assign excitation, coil 500, negative. And then I select the phase B, terminals not assigned to any winding, and I select all of these coil arms, right? So here, these are positive and these are negative direction. This will be the magnetic axis of phase B, magnetic axis of phase A and magnetic axis of phase B. Also, I should select all of aluminum bars and assign the end connection. So for end connection, we need to know the value of end ring resistance. Actually, the end ring bar to bar resistance, the resistance between two adjacent conductors. I know the value from here. Actually, I calculated the value by calculation of the end ring dimensions and calculation of the DC resistance of the end ring. Also, you can consider an operating temperature for the rotor cage to be able to calculate the resistivity of rotor cage at working temperature. So let's copy this and in dynamic simulation, paste the number, the resistance between two adjacent bars. So for excitation of the stator windings, we should create an external circuit. We have two coils, and this is the circuit connections. This is phase A, phase B, and we have a supply voltage here. And the capacitor is in series with one of windings. Here is in series with the phase B. And also because these two coils are identical, we can place it in series with the phase A. But consideration of the position of the capacitor determines the direction of the rotation. When capacitor is here, the current in the phase B ahead of the current of the phase A. So first we have the peak value of field here, and then we have the peak value of field here. So as you can see, direction of rotation is counterclockwise. But if we place the capacitor here, first we have the peak value of current in the phase A, then we have the peak value of current in the phase B. So the direction of the rotation is in this direction, right? So from here in the software, I set the winding type to external. I press OK. Also for phase B, I set it to external. OK. And from here, external circuit, add external, create an external circuit. I press OK. So this is the phase A and the phase B. So from component libraries, I place two resistance here, passive elements, one resistance here, one resistance here, and I need a capacitor also. I place a capacitor here, and we should place a voltage source, sinusoidal voltage source. Let's save the project. This is the circuit file. From here, rotate. Let's do these connections, this connection, and this connection, connections like this. these two coils are in parallel, phase A and phase B are in parallel. And what is the value of resistance? Coil resistance, I calculated the value of coil resistance, and I measured the value of coil resistance using the ohm meter. The value is 492. This is hot resistance, not cold resistance, because also I considered an operating temperature. So here I write 492, okay, and 492, okay. So this is the value of resistance in phase A and phase B. Also, the value of capacitor is equal, as I remember it's equal, right, 2 microfarad. The value of capacitor here, I write 2 microfarad and I press OK. The value of voltage is equal, this is peak amplitude, not RMS value, is 310. The frequency of the supply voltage is 50 Hertz, and I press OK. So, because also I want to know the value of the terminal current, I should consider a current probe. I use the current probe here and rotate, rotate. Let's delete this edge and use this current probe here. Let's consider proper name. I write here IT. That is the value of terminal current. Also, we should consider a ground. In my keyboard, I press Ctrl plus G, right, to place a ground here. And this is our external circuit. We have a source here. This is terminal current, phase A, phase B, and the value of resistances that we have here. So I should save this model and export the model, the SPH file of the circuit. I save it into desktop. I write my circuit. Now in dynamic simulation, excitations, external circuit, I should import the external file. My circuit, yes. So we defined excitation, phase A, phase B, and end connection. Now I should draw the motion band and enclosure. So I draw a circle here. That is my enclosure. I change the name to enclosure. The material is vacuum. Let's change its transparency for a better visualization, 0.9. And I want to consider the diameter of this enclosure 10% or 5% higher than the outer stator diameter. So what was the outer stator diameter? It was equal to 80. So I write here 0.5 times 80 mm. And I press OK. Excuse me, this is radius, not diameter. So I should divide it by 2. Okay, 5% higher. Also, I draw another circle, that is my motion band. the value of radius is equal to the stator bore diameter is 48 mm divided by 2 minus 0.5 mm divided by 2. That is 8 gap radius. So we have this motion band here. I change the name to motion band. Set its transparency equal to 0.9, right? So yes, now I should define the motion band. But first, let's press E on keyboard, select this edge, assign zero vector potential boundary condition, and this boundary condition, zero vector potential, and right, select all objects, assign a mesh operation, length based, let's consider 4. And add a solution setup just to check if we can generate the mesh properly, suitable for the finite element simulation. The mesh generation is completed, and I select all objects, plot mesh, done. You can see the mesh density here in this problem. So why we don't have the same mesh density for the stator? Maybe I didn't select all objects. Let me select all objects. Mesh operation inside for all objects is equal to 3. So anyway, I should regenerate the mesh. So I think it's enough for this video. Let's pause here and continue in the next video by setting the motion band and the definition of the motion and running the dynamic simulation. Thanks for watching.